Good afternoon, student. This is the lecture number 12 of unit number 2, that is Introduction to Instrument Characteristics. Okay, in the previous lecture, we have studied various dynamic characteristics. In that, we have studied accuracy and precision, repeatability, speed of response, measuring lag, fidelity, and dynamic error. Okay, that various types of dynamic characteristics we have studied in the previous lecture. Today we are going to study the next dynamic characteristics, that is overshoot. That overshoot is nothing but the because of mass and inertia of a moving part, the pointer of the instrument does not immediately come to rest in the final deflection position. Okay, the pointer goes beyond the steady state, that is its overshoot. Overshoot is defined as the maximum amount by which the pointer moves beyond the steady state. Okay, now in this diagram we can see the what we can say that the pointer deflection versus time graph. Okay, in this case, as we have stop uh, stop giving the input to the instrument, but whatever the analog instrument we having the pointer given or pointer gives the deflection after removing the input from the instrument. Okay, and that that is nothing but the maximum amount by which the pointer moves beyond the steady state position, that horizontal line. Okay, so this horizontal line is representing the final steady state position, but the maximum amount by which the pointer moves beyond the steady state. Okay, so this much amount the pointer moves beyond the steady state, and this is nothing but the overshoot. In other words, we can say that the pointer of the instrument does not immediately come to rest in the final deflected position, and that pointer moves beyond the steady state line, and that is nothing but the overshoot. Okay, so then next dynamic characteristics we will have to study, that is dead time and dead zone. Okay, so in the given diagram here we can observe that on x-axis there is a units of time, and on y-axis there is unit of measured quantity. Here what is dead time, that we will have to study. Okay, now here the dead time is defined as the time required for an instrument to begin the responding for change in the measured quantity. Okay, so that threshold is nothing but the dead time. Okay, so means the time required for the instrument to begin responding for a change in the measured quantity. Okay, means after supplying the input or after supplying the input signal to the instrument takes certain time, or requires certain time uh, to begin the response to the given input signal. Okay, that is nothing but the dead time. Dead time means what? For that particular time instance, the instrument will not show the reading. That is nothing but the dead time. It represents the time before the instrument begin to respond after the measured quantity has been altered. Okay, means until and unless the means until the pointer will not show the reflection after giving input to the instrument. Okay, and for a time instant for which the means the time instant for which the instrument will not show the output signal, and that time instant is nothing but the dead time. Now what is dead zone? The largest change of the measured the largest change of the measured to which the instrument doesn't respond, the largest change of the measured to which the instrument does not respond. Okay, so here in this diagram we can observe for this uh, change, for this much change, dead time means what? The time for which, sorry, the time instant for which, this is the time instant for which the instrument will not show the reading, and that is nothing but the date time. And time zone means what? The zone within which the instrument uh, change of the measure to which the instrument does not respond. The largest change of the measurement to which the instrument does not respond. Okay, so that is nothing but the dead zone. Okay, so this is nothing but the different dynamic characteristics. Okay, in that dynamic characteristics we have studied overshoot, dead time, and dead zone. Next we will have to study the ramp or linear function. What is ramp or linear function? In figure number 2.7, standard input functions shown in three diagrams, a, small a, b, and c. Okay, so that graph is showing time on x-axis and quantity on the y-axis. Okay, in this case the input varies linearly with time. In the very first diagram we can observe the uh, input, whatever the input we have given to the instrument or measurement system, that follows the linearity. Okay, in this case the input varies linearly with time, input varies linearly with time, and this is mathematically represented by means which is parallel to x-axis and perpendicular to the y-axis. Okay, means what? In this case the input varies linearly with time, and this is mathematically represented by the theta I equal to 0 at t less than 0, and theta I equal to omega t at t greater than equal to 0 versus time relationship. Okay, the next is a next graph which is proportionality. Time is proportional to the quantity, which is again the linear function but having some proportionality between time and quantity. And third one is the sinusoidal and sine wave function, sinusoidal or sine wave function. Here we can observe sinusoidal or sine wave function. Okay, in this case the input as a cyclic variation, the input varies sinusoidally or as a function of sine wave constant maximum amplitude. Okay, here that theta equal to a sine, theta I equal to a sine, here theta I equal to a sine omega t, where a is amplitude and omega is frequency in radian per second. Now when that waveform will start from the origin, when the waveform start from the origin, what will happen, that t, or what we can say that it is on x-axis there is a time, and time whenever the time is 0, in that case the sine function of omega t, that t is 0, then omega t will become 0. See here that omega t is the multi product of w and t. Instead of in that t will become 0, so wt will become 0, and hence sin wt or sin 0 will be 0. That's why theta I equal to 0, hence we will got the sinusoidal waveform at the origin. Okay, then we have increases the value of time maximum. Okay, in that case that wt will become maximum, or we can taken as 90, so sin 90 will be 1, sin 90 will be 1. That's why sin 90 will be 1, and 1 multiplied by a will be capital A, means theta I equal to a. That's why we will get the point here. Okay, again the time function is 0. That's why a sin omega t, or we can say that is 0, pi means 90, sorry, pi by 2 and pi. Is it? Are you getting it what I am saying? Means initially the time is 0, then pi by 2, then pi. Now pi sin omega pi means what? It is approximately again 0, that's why theta I equal to 0. So here we are getting the sinusoidal waveform. Okay, means I think all of you have understood how that ramp or linear function will work, sinusoidal or sine wave function will work. Okay, so then next topic we will have to start, that is zero first and second order system. For understanding the zero first and second order system, we will have to understand what is generalized measurement system. System can be mathematically described by the following differential equation. The differential equation is a n d raised to n plus a n minus 1 d raised to n minus 1 plus so on plus a1 d plus a0 uh, bracket close theta I equal to in bracket bm d raised to m plus b minus 1 d raised to m minus 1 plus so on plus b1 d plus b0 into theta I. So this is nothing but the generalized measurement system expressed mathematically. Okay, where A's and B's are constant depending upon the physical parameter of the system. Means whatever the measuring instrument we are using, that A's and B's, all the A's and B's are constant depending upon the physical parameter of the system. Then d raised to k equal to operative derivative of the order k, operational derivative of the order k, then theta 0, then theta 0 equal to information out of the measurement system, information out of the measurement system, and which is acts as the output, and theta I, that input information. The time factor in the input or a driving function may correspond to step input, RAM input, sinusoidal input, or any combination of these, or any combination of these. The order of the system is generally classified by the value of power of n. Generally, the order of the system is classified as power of the value of power of the n. So zero order system n equal to 0 and a1 a2 equal so on an equal to 0. First order system n equal to 1, a2 comma a3 so on an equal to 0. Second order system a3 n equal to 2, a3 comma a4 so on an equal to 0. So these are the this is the generalized equation for deriving the relation for first order, second order, zero order, first order, and second order system. Okay, means for zero order n equal to 0, for first order n equal to 1, for second order n equal to 2. So by using this relation we can find out the derived form of zero order, first order, and second order system. In zero order system, consider an ideal measuring system, that is a system whose output is directly proportional to input. Which system we are considering? Whose output is directly proportional to input. Okay, and no matter how the input varies, while we are considering the output is directly proportional to input, we don't have to consider the input, means variation of input. The equation of this system is obtained when the power of n is set equal to 0 in the general equation for a measurement system. The input of this system, input of what? Input of this system is obtained when the power of n is set equal to 0 in the general equation for a measurement system, that is a0 theta 0 equal to b0 theta I, or a0 theta o equal to b0 theta I. Means what? Input output is equal to input function. Okay, or theta o, output function, equal to b0 by a0 multiplied by theta I, and b0 by a0 is nothing but proportionality constant k. Therefore theta o is equal to k theta I. here we can say that theta O is proportional to theta I, and that proportionality constant is k. Above equation represent the mathematical equation for zero order system relating output to input. Okay, so this is very much quite simple, as you have studied various differential equation in the M1 and M2. Okay, where k is the sensitivity of the system, or we can say that the proportionality constant of the system, and is only parameter which characterize a zero order system, and is the only parameter which characterize the zero order system, and its value can be obtained through the process of static calibration, and its value can be obtained through the process of static calibration. Static calibration, the process by which we can obtain the process of static calibration. A block diagram representing zero order system is shown in figure. Uh, in the next slide we can see that the block diagram, that is nothing but the theta O equal to BO or B0 by A0 multiplied by theta I, and B0 by A0 is replaced by K, that is sensitivity constant. Okay, so here this type of diagram we have studied in the generalized measurement system of input output configuration, is it? So example of zero order system is mechanical levers. Mechanical levers is used for the lifting mechanism, then assembly mechanism. Okay, then amplifier. Amplifier you have observed as sound amplification device. Then potentiometer, which gives an output voltage which is proportional wiper displacement. Okay, so this is nothing but all the examples of the zero order system. Then next we will have to study the first order system. In first order system, the behavior of a first order system is represented by a first order differential equation, and that first order differential equation is obtained by putting n equal to 1 in the generalized equation, which is obtained when the power of n is set equal to 1. Okay, in the generalized equation for measurement system. Then we have after putting the value of a is a equal to 2, 3, and n equal to 1, so on. Okay, so we will get generalized equation in terms of a1 d theta o by dt plus a0 theta 0 equal to b0 theta I. Okay, by dividing equation above equation by a0, what we will obtain, a1 by a0 multiplied by d theta 0 by dt plus theta 0 equal to b0 by a0 into theta I. Okay, so a1 by a0 is represented by tau, and that b0 by a0, that in the previous that zero order system we have defined as a k, sensitivity constant. b0 by a0 is defined as a sensitivity constant k. That's why tau d theta 0 by dt plus theta 0 equal to k theta I. Okay, where tau is the time constant which is represented by a1 by a0, and k is static sensitivity constant, that is k equal to b0 by a0, and capital D equal to d by dt, and d square equal to d square t by dt square. Okay, or dt square by dt square, d square by dt square. Okay, now uh, we have means that d by dt is replaced by capital T, so that's why tau capital D d theta. See here, where we have here that tau d theta 0 plus theta 0 equal to k. Suppose we have taken theta 0 as common, then t capital D plus 1 out of bracket theta 0 equal to k. Okay, now we have divided the equation by theta I, then we will obtain means theta I by tau d plus 1, means theta 0 by theta I equal to k by tau d plus 1. Okay, so this is nothing but the derived equation for the first order system. Okay, the above equation represent the standard form of transfer operator for the first order system, and its block diagram has been indicated by 2.9, diagram number 2.9. Here the proportionality constant is k by tau d plus 1. Okay, and examples of the first order system are velocity of a free falling mass, is whenever any object is falling from a higher height to a ground, that is nothing but the example of a first order system. Then build up of air pressure in bellows, the next thermistor and thermocouple, resistance, capacitance and network. Okay, these are the examples of first order system. Okay, then we will have to study the second order system. For deriving the relation of second order system, the input output relationship of a second order system is described by a differential equation of the order that n equal to 2. Okay, n equal to 2 and a equal to 3, 4, 5, so on. Okay, then a2 multiplied by d2 by d theta divided by dt square plus a2 d theta by dt plus ao theta 0 equal to b0 theta I. Okay, as we have divided by a0, then a2 by a0 plus d2 d theta by dt plus a1 by a0 d theta 0 uh, theta 0 by dt and theta 0 equal to b0 by a0 theta I. Okay, so by dividing both side by a0, then that omega n equal to square root of, here we have transfer, this is k, this is one another function and this is another function. So wn equal to square root of a0 by a2, that is undamped material frequency radian per second, r equal tau equal to a0 by a1 by a0, it is time constant, and k equal to b0 by a0, static sensitivity. Okay, so the relation we can transform into w 1 by wn omega n square d2 by d2 d square d theta, d square theta 0 by dt square plus tau d theta by dt plus theta 0 equal to k theta I. Okay, so by taking theta 0 as common, so d square by omega n square plus tau d plus 1 multiplied by theta 0 equal to k theta I. So theta 0 by theta I equal to k by d square by omega wn square plus tau d plus 1. Okay, let wn equal to square root of a0 by a2, undamped natural frequency radian per second, psi equal to a2 by square root of 2 in bracket, 2 by square root into 2 into square root of a0 a2, damping ratio k equal to b0 by a0, static sensitivity 1 by wn square, 1 by wn square, k equal to b0 by a0, that is static sensitivity 1 by wn square d2 by dt d2 d theta by dt square plus 2 psi d theta 0 by wn dt plus theta 0 equal to k theta I. Okay, so that is nothing but the derived relation, and we will have to just keep in mind how that three relations come in the second order system. Okay, the other part is simple, quite simple, but these three relations or two relations using the second order system, that we will have to keep in mind. Okay, now the above equation represent the standard form of transfer operator of the second order system, and its block diagram is shown in figure 2.1. Here that input uh, having the derived relation k by d square by omega n square plus 2 psi by omega n in bracket d plus 1 and output equal to output signal. The examples of the second order system is piezoelectric pickup, UV galvanometer, spring mass system used for acceleration and force measurement, then pen control system on XY plotter. So these are the example of second order system. So today we have completed the two dynamic characteristics, that is what we can say that dead time and dead zone and overshoot, and in addition to that we have studied linear function and sinusoidal function, okay, or sine wave function. Then next topic we have studied first order system, second order system, zero order system, first order system and second order system. Okay, so the remaining part we will cover in the next lecture. Thank you.